Hello and welcome to a Maths with Harry lesson. In this video, we're going to have a look at mathematical proof. Now in this video, we're just going to introduce the idea of a proof. You've probably seen proofs before at GCSE, maybe on some GCSE topics, but we need to introduce proof a little bit here. So I'm going to introduce kind of three things that a proof is made up of. Okay, as you can see, I've got three red boxes. And we start with one thing, and that thing that we always start a proof with is known facts, or that should say theorems. Just give me a minute, let me fill that in. There we go. Known facts or theorems. Okay, so to start off with a proof, you may be given a known fact or theorem and you might be asked to prove it. Okay, so that's what you might start with. Then we go across the arrow and we go to the second box that starts with clearly shown logical steps. So we start with a fact, we start with a theorem, we might need to prove that. We do some clearly shown logical steps. Logical meaning they make sense, okay? You haven't just kind of pulled those steps out of thin air. Clearly shown, you have to show those steps clearly. It has to be clear the maths that you're doing to prove this theorem or statement, okay? And then the final part of the proof is a statement of the proof. So it's always nice to finish with a statement of the proof saying I've proved this certain thing, okay? Or, you know, as required. That's what I write quite often at the end of my proof, okay? I've shown the thing that I need to prove, so I can write as required. So those are the three kind of steps of a proof. You start with facts, you start with a theorem maybe, you do some steps, and then you kind of do the statement of your proof. You summarise that you have proved what you need to prove, okay? Now, just one important thing here. A mathematical proof must show something is true in all cases. Now, it's only true if you're being asked to prove it is true, okay? So if you're being asked to prove something is true, then it has to be true in all cases. Just showing one case is true, and we'll have a look at an example of that in a minute, okay? Just showing one case is true, so giving a true example, is not enough to prove it, because there may be a counter example, as we say. And a counter example is something that is not what you're trying to prove. So you could have a proof and you can give an example of that proof being true. If you give an example of that proof being false, so it doesn't work, it doesn't make sense, that proof, you've found a counter example, okay? So when you prove something, you have to prove it's true in all cases. So let's have a look at a quick example. Here I have a statement. It says the product of two odd numbers is odd. And we have a demonstration, okay? We have just one example of that. Now, one example is not enough to prove the statement true. It's just saying, yes, it's true. It might not be true for all odd numbers, but we have an example of just two odd numbers, okay? We can see the two odd numbers that I've chosen here are 5 and 7. Product means multiply, so the product of those two odd numbers is odd. Well, the product being multiply 5 and 7, we do get 35. 35 is odd, so it makes this statement true, okay? So we've got a true statement there. But that, like I said, is just one example. We want to do a proof to show that it is true for everything. And the everything here is all odd numbers. So any two odd numbers that I multiply together will always give me an odd number, okay? So, well, if you've done some work at GCSE, you probably remember doing proofs and you consider even numbers and you consider odd numbers, okay? So let me say in kind of basic wording here, let Q be a number, okay? And maybe we let it be a real number. We don't have to go into too much detail at the minute, but let it just be a number, okay? Then we have 2 times Q. That must be even, because we've multiplied it by 2. And we know that's true. We don't need to prove that, okay? That's almost like a known fact, okay? That's what I've used there. If I have a number and I multiply that number by 2, so 2q, it must be even because any number times 2 is even. We know that as a true fact, so we can use that. We don't need to prove it, okay? So we've got a number q, multiply it by 2 to give me 2q, that is even. Then if I add 1 to that, so I could say then 2q plus 1, is that going to be odd or even? Well, we know 2q is even, and any even number plus 1 is odd. Okay, so 2q plus 1 is odd. Now, that is then going to be an odd number, so I'm going to use that in my proof. But I'm also going to let p be a different number, okay? So that can tell me, and I'll just do it here, that 2p plus 1 is also odd when p does not equal q. Okay, they are different odd numbers. If p was equal to q, then these two things would be equal. But they're not equal to each other, and that's quite important to say, so that we've got two different odd numbers, okay? We know that 2q is even, so that means 2p is even because p is just a number. And then we're adding 1 to that, and we're adding 1 to this to give me an odd number. Okay, so those are two odd numbers. Now, then we're going to go back to the thing that we're trying to prove, the statement that we were told. We were told the product of two odd numbers is odd. So the product, we multiply them. Well, I'm going to multiply this odd number and this odd number together, okay? So when we do that, we will get this, and I'll do it using brackets. We've got 2q plus 1 times 2p plus 1, okay? So then what we do is, well, we just kind of need to do a little bit of algebra manipulation here because we can't do anything with those two brackets to prove that that is an odd number like we're being asked to prove. So let's do a little bit of multiplication. Multiplying out the brackets, I'll get 4p squared plus 4p plus 1, okay? Oh no, sorry, no I won't, that's total rubbish. I will get 4pq, I was thinking they were both p's then, 4pq plus 2q plus 2p plus 1. That's better than what I had before. Okay, so that's what we get when we expand the brackets. Now remember, we are trying to prove that this product here is odd. So we kind of need, if we think about what an odd number is, it's an even number plus 1, just like what we had here. So we kind of need to have, in this case as well, an even number plus 1. Notice that all three of these terms have a factor of 2. So what I'm able to do is I'm able to factorise out a 2 from the first three terms. Let's do that. We'll have a 2 outside the brackets, and then we'll have 2pq plus q plus p, and then a plus 1 outside, okay? Now, we know that q is a number, and so is p. I was following this, but just changing it to p, okay? P and q are just numbers. So what we've got here is we've got 2 times a number plus 1. So this 2 times a number, this is even, because we're multiplying it by 2. And then we've got plus 1. This plus 1 would make this whole number odd. Okay, let's put that there. So this is even because we've got 2 times this number, and q and p are numbers, so it makes this even. An even number plus 1 is always going to be odd. So there's my proof, and therefore we can say, therefore, the product of two odd numbers is odd. not even, it's odd, okay? We've proved. So that's kind of like our third red box above. That is the statement of the proof. We've done a little statement at the end. We've said, okay, here is the statement. Here's my mathematical working. That's why it's called a mathematical proof. And then I've said, okay, well, therefore, I've done the proof, so the statement must be true. Okay, so let's now have a look at proving an identity. You probably haven't seen identities before at GCSE, and you can see on the screen that an identity is this symbol. This is the identity symbol, and we use it in a example where the equal sign is kind of not strong enough. Okay, now what I mean by that is this example here. Let's just zoom in and have a look, okay? I know that when I expand the difference of two squares, I always get this, okay? So what that means is it's always the case. I'm going to expand these brackets to give me a squared equals b squared. So yes, they're equal to each other, but they're actually equal to each other in every single case or every value of a and b. Okay, so we can actually use an identity symbol here. It kind of makes this, instead of an equation or a statement if you like, it makes it an identity. Expand these brackets and you will always get a squared minus b squared. They're identical to each other, okay? So how do we prove an identity? Well, we have 3 steps to prove an identity. Here are the 3 steps. You can start with either side of the identity. Doesn't matter which side you want to start with. It's sometimes easier to start with one side than the other side, and you will hopefully look at the question and maybe guess which side to start with. But if they both look quite easy, or they both look similar in difficulty, then try both. Just try the left-hand side and see whether you can manipulate that into the right-hand side, because that's the second step, okay? You take whichever side you want and you try and manipulate that using algebra until it matches the other side. So if you take the left-hand side and it's an identity to the right-hand side, you do some maths to the left-hand side, and hopefully, if you do it right, you will get the maths that is on the right-hand side. So you'll get them equal to each other. And because they're equal to each other, then you can say it's an identity, because that's what you started with, okay? And then you just make sure you've shown every single step. That third step, really, this part here, doesn't really have to be there, but it's really important when you're doing a proof of anything, really, but a proof of an identity, that every single step follows. The step above must follow nicely onto the step below. There should be no maths that you miss out. Even if you think it's quite obvious, the more you prove, the more you explain in terms of the maths that you're doing is much better than just doing a proof in a few steps, okay? A lazy mathematician is one that misses out steps. You don't want to miss out steps, okay? You want to do as many steps as possible so that you're not wasting time, but so that you're proving the maths as well as you can do, okay? So at the bottom here, this is kind of the proof that I did here for this identity, okay? The difference of two squares is always a squared minus b squared. Well, expand your brackets, this is what you get here. And I always like to write on the right-hand side a little bit of wording of what I'm actually doing, okay? I did that by expanding the brackets. And then we can see these two are going to cancel, so I could just cancel those out, okay, that's not hard. And then we're just left with a squared minus b squared. Look how I carry this identity symbol down with me, because we started with an identity symbol. So we've gone from expanding the brackets here being identical to a squared minus b squared, so the the factorised brackets here must be identical to a squared minus b squared. And I've wrote as required because that's what we needed to prove, that's what we started with, okay, that was the identity. Okay, so not really hard, just quite a lot of algebra manipulation. Right, let's have a look at an example. So, pretty similar to the one we just had. This time we've got 3 brackets. So, you can actually start with either side of the identity. It doesn't matter which side you start with. However, I would suggest you do start with the easier side. I think the easier side here is the left-hand side, because all you really have to do is expand the brackets on the left-hand side. If you started with the right-hand side, what you need to do is factorise, and let's not bother with that, okay? We will not bother with factorising that. So let's have a go at proving if you can expand the brackets, do some manipulation, and hopefully you get what you have on the right hand side. So pause and have a go, and then I'll work through the answer. Okay, hopefully you're quite good with algebra, because all we have to do is expand the brackets. I'm going to do the left hand side, so I'll write LHS for left hand side because that's what I'm starting with. So I'll just write the left hand side down in my working. We've got that, and I'll do some expanding. I'll expand the first two brackets, and I'll use identical to, because it is, we're just doing some expanding, okay? So the first two brackets, when we expand them, we'll get 3x squared minus 15x plus 2x minus 10. And it's always important just to double check that that is correct. So double checking that, make sure you kind of do your expanding in full. Don't try and simplify in your head, because that's where mistakes start to show. So 3x times the x gives me 3x squared. There gives me the minus 15x. There gives me the plus 2x and the minus 10. And now you can simplify, so it makes it easier to expand with the third bracket. So 3x squared, we have got minus 13x minus 10, and then times x plus 7, okay? Then expand your bracket. Hopefully this is not too hard. We're going to have 3x cubed plus, what's that going to be, 21x squared minus 13x squared. And what is 7 times 13? Let's have a look what that is. I think is that... What's that going to be? Let me double check that with a calculator. It is 91. So we're going to take off 91x there, okay? In an exam, you might want to do a bit of side working if you want. So we get 91 there, then you get minus 10x, and you get minus 70. Okay, let's double check that we've done that correctly. So we have the 3x squared with the x, gives me the 3x cubed. Plus 21x squared minus 13x squared minus 91x minus 10x plus minus 70. That's perfect, okay. And then we want to just collect like terms. So there's only one cube there, and it's 3x cubed. The 21x we're going to take off to give me plus 8x squared. And then minus 91 minus 10 is going to give me minus 101. Perfect, and that's an x, and then minus 70. That is exactly what we needed on the right hand side. You can see, if I highlight what was here on the right hand side, we have kind of done our expansion, collected like terms, and that is exactly what we needed. So what we've done is we've done our logical steps. We've started with our statement, if you like. It's not a known fact here, we're just proving an identity. We've started with this, okay, our 3 brackets. That's the left-hand side, so we chose to expand them. We follow our identity along here, because we know expanding keeps it identical. So expand your brackets, then you've got this third bracket, collect your like terms, then expand that third bracket, and then collect like terms, and I can see that that is identical to the right hand side, okay? So I sometimes write this, and so we have the left hand side is identical to the right hand side, therefore identity proved. Okay, that's a little bit of shorthand. You could also say, therefore, this is the case. But really what I've done is I've got the left-hand side, I started with that, done my algebra to finish with the right-hand side, so the identity must be proved. Okay, let's have a look at the second example for this video. It says, prove that if x minus p is a factor of f of x, then f of p is equal to 0. think back to the last video, what this is actually asking you to prove is the factor theorem. Okay, the factor theorem says two ways. This is the first way of saying the factor theorem. If x minus 1 is a factor of f of x, then if we substitute, x minus p is a factor, if we substitute that p into f of x, we get 0. You could also say it the other way around. If f of p is 0, then x minus p is a factor of f of x. Okay, I've got a little hint here. It says consider f of x being equal to, so this function being equal to its factor x minus p times another function, because that's what being a factor means. We can factorize out x minus p from f of x to give me this other function there. Okay, so think about what you can do with that. Maybe you could do some substitution. If you're not sure, then continue watching and we'll work through the answer, but have a go if you want to. Press pause and then press play when you're ready for the answer. Okay, the first thing I'm going to do is I'm going to do some substitution, and I'm going to substitute p into this hint. Okay, this hint works because really, if you think x minus p being a factor, I'll do some working here. Okay, x minus p, and I'll just put a factor of f of x, then what that means is we can divide x minus p into f of x and get a nice function. Okay, if you think back to the factor theorem, so f of x divided by x minus p gives me a nice function. If you were to do algebraic division on this, grid method or your long division, okay, if you were to do that, then the x minus p would go in nicely, and because it's a factor, you'd have a remainder of 0, and then you'd just take your quotient. G of x would be your quotient, okay? So what I'm going to do to start the proof is I'm going to use this piece of information here, okay? We're saying prove that if this is true, so x minus p is a factor of f of x, then this is the case. So this then bit I'm not going to use for the minute, okay? We're going to try and prove that. I'm going to use this because it's saying if this is true. If this is a factor of f of x, then that's information there at the end is true. So let's do that, okay? Let's let x minus p be a factor of f of x, okay? Then we can use the hint from what I did on the right hand side here. Then we know that f of x is going to be some function multiplied by x minus p, because x minus p is a factor. So if I then substitute p into there, what am I going to get? Let's think about that. So substitute p. Wherever I see an x, I'm going to substitute that with p, okay? So let's x be equal to p. That's going to basically work out, that will give me, okay, f of p, because I'm just substituting p into wherever I see an x. Okay, so we'll have f of p is equal to, and then I'm just going to put p wherever I see an x. We'll have p minus p multiplied by g times p. Okay? Well, I don't know what gp or g of p is, and I don't know what f of p is, so they're just going to stay the same. But what I do know is that. I know that that's a little bit of an error, if you like, or not an error, it's quite important. It changes what I have on the right hand side. P minus p is 0. So that is equal to 0 times g of p. 0 times anything is 0, and so we have that is equal to 0. Therefore, we have f of p, just taking the f of p from there, is equal to 0. Okay, so that's my proof complete, really. All I had to do was use the proof, and I'm going to use this piece of information because it's saying if. It's also saying if this is true, prove that then this is true. If x minus p is a factor, okay, so if it is a factor, let's say it's true, which I did here, let it be a factor, then we can use that hint. We want to then say that's true, so then f of p equals 0. Well, how am I going to get that? How am I going to get 0 on the right hand side? Oh, well, looking now, I can see it's when x is equal to p. But I also got that to work out f of p as well, okay? F of p on the left-hand side here. Do some of your algebraic manipulation, is clearly going to give you 0. So you've proved what you need to prove. So I could say, so if x minus p, that's just a little imply sign there. It's just kind of how I like to write my statement at the end. All of that proof implies that the statement is true. So if x minus p is a factor of f of x, so that if that's true, then this is also true. Then f of p is 0. And that's my finishing statement.